So I'm going to talk about something that's sort of I know this is an MPC conference, and I have something that says ZK on the first slide, so maybe that's already a faux pas. But a lot of what's in here applies equally well to MPC. It's going to be more about this is going to be more of a theoretical talk about what sort of economic guarantees you can get formally when you add in other types of covenants or constraints to classical mechanisms like auctions and other things like that. I think the main point is that, hey, there's a lot of other applications of MPC and ZK that aren't just, hey, we're making another virtual machine or consensus or trading type of thing. And so hopefully this inspires some of that. So ZK and FHE and MPC, I should have added an MPC. Promise a lot. I guess we just heard a little bit. I guess we didn't talk about privacy preserving machine learning, but in general, that is sort of one of the long-term goals. Of course, with the revolution in IVC proving this year, this is another thing that's sort of been promised and kind of people have been claiming we'll have tomorrow. And then, of course, the syncness and sort of all your standard complexity stuff. The problem is none of these are particularly good concrete benefits. Like, I bet you no one here could convince their relatives that any of those three things are useful. If you can, one of your relatives works in those fields. In some ways, I think the utility of privacy preserving technologies has been quite poorly conveyed to people. Partially because if I tell you that, hey, look, ZK is great for compressing a blockchain, that's not a very tangible benefit to a user, right? Maybe the user is like, hey, my fees went down, my confirmation time went down, ... But it's not a particularly direct economic benefit to them. And yeah, this tweet, I think, demonstrates people kind of flogging descriptions of ZK. Okay, so this is the main question to ask, which is, are these technologies kind of always going to be only things that are appreciated by the technical cognoscenti? And I will talk a little bit about verifiable mechanism design as an answer to something where the average user can see the real benefit of the thing they're working on. So one thing to note is, I think especially in 2019 through 2021, there were a lot of projects and things kind of created on the idea of like, hey, just add a T, ZK, or MPC, and you'll suddenly solve all these problems. You'll make front running much less profitable. You'll make some of these auctions hard to manipulate. You'll be able to do something like private machine learning. But this is not really true. So for instance, in Uniswap style dexes, you effectively have this problem where in order for anyone to use anything in finance, you have to have some notion of public data, whether it's a price, interest rate, fees. And if you want to make some of the data private, you still have to compute some public posted type of value. And the question is, can you actually take the public data, like the sequence of prices, and infer something about the private data? And for Uniswap style things, you can show that you can actually uniquely, the fact that I can post the algorithm in the slide tells you that there's a way to uniquely infer people's private balances. And this comes from the fact that it's sort of easy to arbitrage, but that also means it's easy to invert the function from that maps private data to public data. Another question you might say is like, hey, why don't we just do ZK sealed bid second price auctions, because then maybe you'll have all these benefits that people want. And so kind of a trilemma that was proved by economists only in 2019 and was sort of the only other time I've heard non-decentralized systems people use the word trilemma, is sort of the auction trilemma, which says that there's sort of three properties you want in an auction. The first property is buyer incentive compatibility. That means that people bid what their true value is. There's no incentive for them to collude to shade their bids or to give bids that are different than what their true value for the object is. The second is seller incentive compatibility. Seller incentive compatibility means that the auctioneer can't add fake bids or censor bids and increase their revenue in some manner. And the third is bounded communication complexity. So that means that I don't have to interact with the bidders, and auctioneers don't have to have many rounds of communication. It's actually provably constant. It doesn't scale with the number of bidders, assuming asymmetric channel. And so you can show that you can't get all three of these. And there were a lot of people, I think, for a while who were sort of claiming, hey, look, if I did a second price sealed bid auction, like I'll get all three of these. And I think especially in the early days of MEV auctions, that was sort of something people said, which turns out not to be true. And the last thing I think is like fair ordering, which is kind of this idea that like, hey, look, we can use some cryptography to help enforce some covenant like time priority or first come, first serve. But it turns out that like those also have these kind of economic changes. So just throwing cryptography into having people vote on orderings doesn't really get around the problem that there may be some very unfair orderings economically to people. And yeah, we proved sort of some errors and possibilities style thing for this. Okay. So all of these are kind of negative. They say, hey, look, people trying to throw cryptography, black box at these kind of incentive problems were unable to really solve them. However, if you actually do combine the privacy preserving technologies with particular styles of incentives, you can get around some of these bad results. So the first type of result, which comes from a paper from this year from Canetti Fiat, can't pronounce the last name, is basically this idea of can I prove to you that a particular price from an auction mechanism is correct by having ZK commitments to both the initial mechanism and having a couple rounds of the bidders and sellers interacting. And you can basically show that for particular types of mechanisms, like the VCG mechanism. The VCG mechanism is the Vickrey-Clark-Gross mechanism in type of auction. And that type of auction is an auction where what imagine the auctioneer was omniscient, knew everyone's utility function, which obviously not realistic, but this is for the thought experiment. And people bid based on that utility function. The auctioneer's price that maximizes welfare for all the participants is to charge the externality, the total externality that the winner causes on the loser. So let's say there's 5 people, and I value the item at 10, someone else values it at 9, someone else values it at 8, someone else values it at 7, someone else values it at 6. If I win and I'm the bidder who values it at 8, because maybe I randomized my bid, then I've caused an externality of size 2, 1, -1, and -2. So the auctioneer charges a price of 0 for the net externality. This is sort of a way of saying like the winning bidder in this type of auction, if you're maximizing the welfare of the auctioneer and all the bidders, has a distinct pricing mechanism. And so the interesting thing you can show is that for this type of pricing mechanism, there exists a way of using ZK to get around the impossibility result I said earlier. The second thing, which is sort of somewhat, I think is a buzzword that still has not been sort of formally defined mathematically, is this kind of notion of intents for expressing preferences across multiple domains. So, maybe I want to trade between asset X and asset Y on multiple chains, but I only want to do it under some conditions. How can I guarantee that type of execution? And one thing you can show is that using commitments and also some minimal ZK proofs of sort of certain constraint inequalities, you can get a larger set of these preference expressions. If you look at the naive set of preference expressions you can get, it's quite small. It has to have everyone's value distribution utility functions have to have a lot of particular properties. But if you have some form of commitment and proofs of particular inequalities, you can grow that space. Another thing that you can do if you actually are able to have users provide proofs of particular types of covenants is being able to give provable guarantees on the fee revenue split in different types of auctions. So right now, if you look at Flashbots today in 2023, there's really two auctions going on. The first auction is what's called MEV-share. MEV-share is a sort of thing where particular applications are auctioning off rights to reorder transactions into them. And then there's, of course, the block auction, which is run by MEV Boost, where the proposer runs an auction on every block and selects from the set of block builders who the winner is. One question you might ask is, how do those two split revenue? So say Uniswap runs a MEV-share auction. That MEV-share auction is, hey, for any transactions that touch the Uniswap call site, you're bidding on the right to be the first one to that. And there's a sense in which what you're doing is a hierarchical auction. You're doing an auction per smart contract and then an auction for the entire block, and you're aggregating the two of those. One question you might ask is, how do I split the revenue between them? Because there's a sense in which if I bid on the whole block, there's a fixed amount of revenue. There's a sense in which if I have auctions for every application, there's a certain amount of revenue. And should Uniswap get some of the full block revenue or not? And if so, how do you prove those rules are guaranteed? And that's sort of a thing that you can do with particular ZK covenants. And finally, a sort of what I consider the most important benefit of using ZK in mechanism design is what's called auditability. So we're used to thinking about verifiable compute. I have a state machine, I have a transaction. I prove to you that the state update of applying that transaction was done correctly according to some rules. But we don't have some way of saying anything if the transaction is invalid. So if I have an invalid state transition, can I say something about what actually caused the invalid state transition? And you may think that, hey, look, the model for ZK doesn't have a way of, it's not a co-NP thing, right? It's an NP particular type of thing, right? So maybe there's no way of saying something about non-inclusion. But there's an interesting thing that for a lot of economic mechanisms, there is a way of measuring this notion of auditability of like how many people actually cheated. And so you could imagine I have a state machine that's representing a first price auction. The one question you might ask is, how much do the bidders have to communicate with each other to figure out if they were if there was some subset of people who were colluding to bid shade? So what bid shading means, which is a slight detour, but is imagine we have 5 people bidding in an auction, and the 5 people all have value $5 for some item. But imagine they communicate with one another and say, actually, we should all just agree that none of us are going to bid above 4. That's a sort of notion of like, hey, I did an invalid state transition. People have colluded to kind of change the outcome of this auction. So one question you might ask is, how much do, let's say one of the bidders was honest, how much communication do you have to do to figure out that that was happening? And you can show sort of in classical results that it's a constant amount of communication, but for a second price auction, it actually involves every participant talking to one another. But with particular types of ZK covenants, you can actually audit who cheated in a much smaller amount of communication. And this might all seem theoretical, but the Department of Justice's suit against Google for antitrust in their auctions, in fact, talks about this, and they have this auditability problem where Google there's a second price auction, which they're running for online ads, and the way you manipulate a second price auction is, as the seller, as the auctioneer, you add a bunch of fake bids. So a second price auction is, I have a bunch of people who bid. The person who bids highest pays the second highest price. So if you're a malicious auctioneer, you just add a bunch of fake bids above the second highest price so that it deforms to a first price auction, so that the winner is basically paying what they're bidding. And Google was doing this, but it took almost 10 years of analysis of historical auction prices to figure it out. That's a very bad form of auditability. The fact that it took 10 years to find that is crazy. And so auditable mechanisms are actually quite important. So I'll probably just skip through this. One thing I would say is like, I think the UX for ZK is pretty abysmal right now. And hopefully things like coming up with these metrics like auditability or confidence intervals on whether particular fees or prices were not manipulated is going to be important in the future. And I think, yeah, like I said, we talked a little bit about order flow auctions, but I also think matching markets, so that's this intent type of stuff, and some of the auditable AI and verifiable AI stuff applies. And here's a list of problems, but honestly, I think we could probably just go to conclusions, which are, these technologies are useful within mechanism design because they can give you particular, very strong guarantees. These types of guarantees are actually things the average user gets a tangible benefit from. It's not just, hey, my blockchain was compressed. And this notion of auditability as sort of the successor to verifiability is one of the things that I think is the most important reason to pursue these technologies. And with that, I'm done.
Thank you. That was not a faux pas. Actually, we had a doc on ZK and snarks yesterday by Yindong, who's right here from Geometry. And literally, I think Waking Next is going to talk about how blazingly fast ZK is. So that was a great doc. Does anyone have questions? We see a hand there.
Hi, thanks for presenting so many interesting points, but I'm trying to connect the dot here. So basically, the ultimate goal of the distributed protocol that we are trying to build with cryptography is that you want to replicate a centralized entity, for example, the exchange or the settlement and clearing houses, right? So these points that you present are features that you think basically the centralized entity is not sufficient. So you want to augment these features into them. Or like the distributed program is so inefficient that we have to replicate a relaxed entity, and then these are the important features that you don't want to miss in the replication.
Yeah, that's a good question. I think it's sort of both of those. So one case, right, is like imagine, and obviously given how slow the wall clock time of all the stuff we're talking about here is right now, this is a not practical thing, but imagine that Google actually did run second price auctions with some sort of collateral system where in order to place a bid, you had to post collateral, and it was sort of on a public blockchain. And if they didn't, and then they had to do kind of this commit reveal plus a proof of inequality type of thing. Then in theory, you wouldn't have any trouble verifying that they actually cheated in their auction. You would have all the public data. So the centralized entities already sort of don't really care about this, right? And the fact that, governments take 10 years to build cases against them is sort of a good sign that people do want this more. But the second thing is for a decentralized network, you may actually want these as first-class citizen, right? You may actually want it to be built in with the idea that any execution trace of a particular mechanism, the economic properties of it can be validated post hoc. Does that make sense?
Are there any more questions? I see a hand too. Here? One here? Yeah.
Thank you for the great talk. Quick question as to how this relates to some of the work in like accountable blockchains and so on, where there are ZK proofs and so on, but it's more about if somebody were to cheat, then it's built into some of the cryptographic primitives and pieces that they look at. I'm not sure if you've heard of some of the work done by, I think it was Seth Gilbert and other people at NUS looking specifically at accountable blockchains. How does that fit with some of this work?
Yeah, so I'm not super familiar with that. If I do remember vaguely reading a little bit about this in terms of it's more for like accountable slashing rules and like for validation. Yeah, this is more just about like economic mechanisms where the ZK pieces give you like pricing guarantees, or like they give you some sort of like manipulation guarantee. So it's more about like, how do I get an economic kind of measurement, like, hey, the price can't deviate by more than X%. And if it did, then you know someone cheated, style things, which do depend a lot more on the particular application. So these are sort of like application-specific type of things, versus that sort of like generic validation. Yeah.
Does anyone have any more questions? I see a hand there.
Yesterday there was discussion about the sealed bid auction, and it's one of those applications that hasn't been leveraged in many places, but I wonder whether there is a place for sealed bid to be used as a mechanism to prevent this gaming of pricing.
So kind of one of the things I mentioned earlier, there's this impossibility result of seller incentive compatibility, buyer incentive compatibility, and communication complexity. That the sealed bid doesn't kind of get around that, because the auctioneer who's running the sealed bid auction can add their own fake bids, right? So if it's a second price auction, as an explicit example, suppose I have two bidders bidding in a second price auction. One bids $10, one bids $9. If the auctioneer is honest, they give the person who bid $10 the item for $9. But if the auctioneer is dishonest, they add fake bids at 9.999, because then they force the person who bid 10 to pay 9.999 instead of 9, right? So the sealed part doesn't get around these incentive constraints. And I think that's sort of the point of this, is that in order to actually enforce these incentive constraints, you also need to have collateral systems where the people participating have to put up some collateral, and then they get slashed based on some rules. And how much collateral they have to put, and sort of like how you do those slashings, that sort of pricing gets enforced by some of these ZK covenants. So you're like showing that like I have an interior point of a semi-definite program or something. That's sort of the style of results that they use for that.
And here? Yeah. Luis?
Thank you for the talk. When you consider using ZK and FHE, are you considering solutions where none of the bids is revealed in the end apart from the winning one?
Yeah, this is a great question. So in the paper that I wrote, that I cited from earlier this year, I'll open it. This paper, the credible optimal auctions. Credibility, by the way, is the economics term for seller incentive compatibility, that the seller doesn't fake stuff. Here we actually assume that you provide a ZK proof that the amount of collateral you have is greater than your bid, but you don't have to reveal it. So you could think of it as like all the bidders, they post a commitment to a bid, then they also post a ZKP that their bid is greater than some collateral in a shielded pool. So imagine I have a shielded pool, which is all of the bidders' collateral. You can't see the total size, but they can generate a proof that the amount of collateral they deposited, like the note that they have, satisfies this constraint that it's greater than bid.
And would there be cases where it's useful to have a result that is actually itself not revealed to everybody, but everybody can still be assured that the bid was properly, the auction was properly done? Yes.
We definitely didn't study that. We effectively have a reveal at the end. It's a very good question of like, can you get better, tighter economic guarantees? The guarantees here are sort of somewhat abstract. What it is imagine that every bidder has a utility function, and based on that utility function, they sample a value that is what they bid. And the question of these credible optimal auctions is, how big is the space, the function space of utility functions that you can satisfy? And there's a way of quantifying those. And your point actually is, can you make that space even larger if you had this fully non-revealed? And that, I don't know.
Thank you. Just a final very quick comment. It looks like in some cases, MPC might actually be the tool to go for. Better than ZK and
Yeah. That's a very fair point.
Okay, if no one else, is there any more questions? No more hands? Can I ask something naive from your last slide?
Oh yeah, sure.
In the last slide, you mentioned MEV being the laboratory. My question is more like yesterday we were littered with questions. We did everything from FHE, ZK, Starks, MPC, secure MPC, HTSS, hierarchical, everything. Why is MEV the laboratory? I feel like I know the answer, but I want to hear from you.
So basically, the only things where people are running in production, like live systems that are getting manipulated effectively, is this. And so it becomes the space where each time you have a new system for reducing a particular type of manipulation, you can actually go test it and see if it actually matches what the theory is, right? Like one of the reasons Flashbots and others are moving to TEs is that they effectively know that there's a ton of problems with the current auction system where you can basically see, you can ping all the relays and get all the bids, and there's actually some observed bid shading where basically the largest block builders are effectively colluding to lower their bids on average because they all know what the value of the block is, and you can publicly verify that no one else is bidding higher than X, so they also don't. So it's not even a sealed bid. And one really amazing incident that I highly recommend reading the postmortem of is the April 2023 consensus bug, where there was basically a malicious proposer who took advantage of the public transparency of looking at everyone's bids in an Ethereum block, and basically observed all the sort of MEV searchers who submitted a bunch of sandwich attacks. And then they were the proposer at that round, so they were willing to take a slash to equivocate, propose another block, which removed everyone else's MEV and actually like front run the front runners and caused this like $11 million loss. So these things have happened in practice where the lack of privacy, the lack of like commitment style devices actually inures quite large losses. So, I'm sure it's not fun to be the person losing money in those things, but like I said, it's good for the cryptography.
Yeah, MEV is like an active Petri dish. Do you ever foresee a future where, I don't know if it's FHE because of how heavy it is computationally or what have you, is actually capable of preventing something like front running? Because the attacks just get so much more sophisticated.
Yeah, so for better or worse, another thing that I guess I didn't cover is, one more recent paper I wrote is on co-authored, was on sort of lower bounds to how much you can reduce MEV. And there's sort of some sense in which, for a generic payoff function, you can't really completely remove it. For something very local, like a sandwich attack, you can, but for something very non-local in like its dependence of transaction ordering, you effectively have a lower bound on how much you can really remove. So in some ways, people have sort of accepted that, I think, and have been moving towards these kind of like, I will write custom ordering rules for my particular application style things right now.
I mean, for now, because MEV is not mainstream. Imagine MEV in everything institutional. That's when you really, truly have to actually try. But like
you can argue that this Google thing was like the ultimate MEV.
It's true, though. Yes. I mean, MetaMask. I was pretty surprised with the MetaMask. I didn't know of that story. I need to read up on it. We'll also ask you later and tweet it out so that everyone can take a look on the paper. But yeah, thank you so much for your time. Thank you.